In this video, we will talk about specific heat capacity. First, we will look at the definition of heat and introduce the sign convention associated with heat transfer. Next, we shall look at the specific heat capacity. We shall give the definition of specific heat capacity and interpretation of specific heat capacity. We shall see how heat and specific heat capacity are related. And finally, we will solve a few problems based on these concepts. Heat are usually represented with the letter capital Q. It can be defined as follows. It is energy transfer between two bodies due to temperature difference between them. The SI unit to quantify heat is joules, the same unit that we use to quantify energy. Now let's look at some sign convention associated with heat. In this diagram, we have a body whose temperature is T2, say in degrees Celsius, and it is placed in a surroundings, let's say in a room, whose temperature is T1 degrees Celsius. Let's assume that T1 is greater than T2. That is, the temperature of the surrounding is greater than the temperature of the body. Since the temperature of the body is below than that of the environment, heat is absorbed by the body until thermal equilibrium is reached. So the body gains energy as heat. In this case, the Q is taken to be positive. And once the thermal equilibrium is established, the final temperature of the body T will be greater than T2, but less than T1. It will be somewhere in between T2 and T1. Now let's assume the temperature of the body is greater than the temperature of the surroundings. In this case, the heat Q is lost by the body to the environment until thermal equilibrium is reached. And we say the body loses energy as heat. And when this happens, Q is taken to be negative. The third obvious case is when the object has the same temperature as the environment, T1 equals to T2. And in this case, there is no energy that is transferred as heat. So Q is 0. And we say that the body and the environment is in thermal equilibrium. Next, let's look at specific heat capacity. The symbol that we usually use to represent specific heat capacity is little c. The definition is as follows. It represents the amount of heat in joules that is required to raise the temperature of 1 kg material or an object by 1 degree Celsius. So the SI unit for specific heat capacity is joules per kg per degree Celsius. As we explained in our previous video, since the size, the range of 1 degree Celsius is the same as the range of 1 Kelvin, then the unit for specific heat capacity can also be expressed as joules per kg per Kelvin. To understand specific heat capacity, let's look at an example. Let's take water. The specific heat capacity for water is about 4,200 joules per kg per degree Celsius. Now what that means is, if you have 1 kg of water, so here you have 1 kg of water, and you want to increase the temperature from, let's say, 18 degrees Celsius to 19 degrees Celsius. What it means is the amount of heat that you have to supply in order to do that is 4,200 joules. Another example is aluminum. The specific heat capacity for aluminum is about 910 joules per kg per degree Celsius. So what that means is if you have, let's say, a block of aluminum whose mass is 1 kg, And you want to increase the temperature of this 1 kg aluminum block by 1 degree Celsius. Let's say from 15 degrees Celsius to 16 degrees Celsius. What that means is you have to pump in 910 joules of heat in order to reach this objective. So what this means is, roughly speaking, it is easy to heat up aluminum than water. So what is the connection between heat and specific heat capacity? Say that you have an object with mass m kg and specific heat capacity of C, and you want to increase the temperature of this object by delta T degrees Celsius. So the amount of heat that you need to put in, Q, is quite simply given by the mass of the object, m, the specific heat capacity of this material that forms the object, C, and the temperature difference, or in this case the temperature increase. So since the temperature increase is given by the final temperature minus the initial temperature, and the temperature is actually increasing, delta T is greater than 0 or positive, and therefore Q is positive, as we have seen in our sign convention earlier. Likewise, if you want to decrease the temperature of this object by delta T degrees Celsius, so in this case your delta T is negative because now the temperature, the final temperature, is less than the initial temperature, you have to extract heat out of the object. So in this case, of course, the heat becomes negative, following the sign convention introduced earlier. So this is an important equation that we will be using in the rest of the video. An important thing about the heat associated with specific heat capacity, the thermal process involved is accompanied by change in temperature. Let's look at a following simple problem. An object designed to operate 150 degrees Celsius contains 1.2 kg of aluminum and 0.5 kg of iron. How much heat is required to raise its temperature from 25 degrees Celsius to 150 degrees Celsius? The specific heat capacities of aluminum and iron are 910 and 470 respectively in SI units. The SI units being joule per kg per degree Celsius. Note that this object contains aluminum and iron, so we have to apply this equation mc delta T 2 times, one for aluminum and one for iron, and then just sum them up. So the total heat is given by the following. Let's do the aluminum first. The mass of the aluminum is 1.2 kg. Specific heat capacity of aluminum is 910. The temperature difference, or the temperature increase rather, is 150 degrees. That's the final temperature. And the initial temperature is 25 degrees Celsius. Now to that we have to add iron. So the mass of the iron is 0.5, specific heat capacity of iron is 470, and the temperature increase is given by, again, 150 degrees Celsius minus 25 degrees Celsius. And when you sum these two positive terms, it is positive because heat is being pumped in, because the temperature is now increasing from 25 to 150, and you will get the following for the value of Q: 165,875 joules. And that solves this problem. Problem 2. A 2 kg aluminum block is heated to 92 degrees Celsius and then transferred into a 6 kg water at 6 degrees Celsius. Assuming no heat loss to the surroundings, find the system's equilibrium temperature. Specific heat capacity for aluminum is 910 joules per kg per Celsius, and specific heat capacity for water is 4,190 joules per kg per degree Celsius. So what happens? At the initial state, you have a 2 kg aluminum and the temperature is 92 degrees Celsius. At the same time, you have a sample of water at temperature of 6 degrees Celsius. So what do? You transfer this block into water. So the final configuration looks something like this. Water, aluminum block inside. So we can expect, in the case of aluminum, the temperature to go down from 92 degrees Celsius to some unknown temperature, capital T, which is what we are interested in. In the case of water, the temperature will go up from 6 degrees Celsius to that same temperature, capital T. So for aluminum, a certain amount of heat is lost, and for water, the same amount of heat is gained. Because there is no loss of heat to the surroundings. So you see, when energy is lost, heat is lost, it assumes a negative sign, and when heat is gained by a system, it assumes a positive sign. So in this case, the absolute values are the same, so the sum is 0, because there is no heat loss to the surroundings. Let's calculate the amount of heat that is leaving the aluminum block. So the mass is 2 kg for the aluminum, the specific heat capacity is 910, and the temperature difference, the final temperature, is the unknown temperature T. The initial temperature is 92. Now note, this is a negative quantity because T is less than 92. To that, we have to add the heat gained by water. The mass of water is 6 kg. The specific heat capacity of water is 4,190. And the temperature difference, so the temperature increase, is the final temperature minus the initial temperature, which is 6 degrees Celsius. So this is a positive quantity because T is now greater than 6 degrees Celsius. And as we have explained a few minutes ago, the sum is 0. So let's group the terms with T. That's going to be 1,820 T. That is that term right there. Plus 25,140 T. That is that term right there. The independent T terms, this times that. That's a negative term right there. Minus 167,440. Followed by another T independent term, this times that. That's going to give you minus 150,840. And the sum is 0. And now you can solve for the capital T. And T will be 11.8 degrees Celsius. So this is the system's equilibrium temperature when the system reaches thermal equilibrium at the end. And that solves the problem. Thanks for watching.